Let's get into entropy of chemical thermodynamics. Now, entropy designated by S. Entropy is molecular disorder or randomness. Now, we know that every body has internal energy U, and that is what is randomness, which I have already presented in my earlier videos. Internal energy U, which is the vibration which it exists. This vibration could be linear, could be rotational, could be wagging, could be any way. It could be wagging, it could be rotational, it could be just simple vibration, whatever. So that's the internal energy a body possesses. Alright, so entropy talks about all that. Now, best example that I can think of is ice getting converted into water, water getting converted into steam. Okay, so ice, if I say S1 is entropy in ice, S2 is entropy in water, and S3 is entropy in steam. Obviously, entropy, that is disorder, in ice is much lesser than disorder in water, whereas in water the disorder is much lesser than in steam. Got it? Got the concept, right? So here the difference S2 disorder here is more, so it is S2 final minus initial. S2 minus S1, that is S2 minus S1 is entropy change or disorder change in this. Let us assume it to be 1. Alright, now when it goes from water to steam, the disorder is say S2. The change in disorder or change in entropy is S2, that is S3 minus S2. Final minus initial. Entropy in steam minus entropy in water, that is del S2. Alright, now here another thing I need to tell you is disorder here is positive. Entropy change here is positive. Entropy change over here is positive. Why? Because we know disorder in water is much more than disorder in ice. Again, disorder del S is positive here, and it is positive, but it is highly positive. Why? Because disorder in steam is much more than that in water, whereas in case of ice and water, in water disorder is more, but it is not that very higher than in ice. Alright, okay. So what we can conclude is entropy change in second state is greater than entropy change in first state. Fine. So this is justly to make you aware about how we deal with entropy. I hope the concept of entropy is very clear. The disorder. Alright. So from this what we conclude is that greater the disorder, larger the entropy change. So here greater the disorder, here to here the change in vibration, there maybe the vibrations where internal energy was like this, here it was like this, whereas here it would be like this. Alright, so change in disorder, greater the disorder, larger the entropy change. So I hope this concept is very clear about disorder. Now let's get into a formula for change in entropy. A change in entropy is equal to Q reversible upon T. Now Q is what? Q is amount of heat transferred to the system. Amount of heat transferred to the system. That is what is Q, amount of heat. So we supply Q to ice, it gets converted into water. Why reversible? If I remove that heat, it would again get back to ice. So reversible. Same way, if I supply heat to water, it would get converted to steam. Reversibly, why? Because if I take out that heat, that would again get back to water. So reversibly, amount of heat transferred, which is reversible heat. Alright, and divided by temperature. T is temperature at which Q is being transferred. Alright, and T is always in Kelvin. So this is the formula which you have got to keep in mind for entropy change. Now yet another issue. The reaction would be spontaneous. Spontaneous means would be going this way, provided del S is greater than 0. that is del S is positive. So spontaneous process, del S is positive. Del S when is positive, only then the reaction would be spontaneous. The process would be spontaneous. Fine. Now, if that's the case, then there shouldn't be any condensation happening. Why? Because see, here entropy is much more, here entropy is much less. So let's come back here. In this case, steam to this, as per this, no. Del S is less than 0. Why? Because entropy here is much lesser than entropy here. So if I call this as, this becomes now S1 and this becomes my S2. This is the final state. So S2 minus S1 would be less than 0 or would be negative. Would be less than 0. Why? Because S2 is much, the disorder in water is much lesser than disorder in steam. So S2 minus S1 would be negative, or del S would be less than 0. So then how? What does this mean? So then what happens? To our rescue comes second law of thermodynamics. Now what does second law of thermodynamics say? Let me explain this first and then come to the law. Del S total, that is entropy change, is equal to entropy of system, this is all system, plus entropy of surrounding, has to be greater. So we introduce another term called as entropy of surrounding. Alright, so entropy of surrounding also comes into picture. Now we are concerned purely with system, but we are introducing surrounding also into it. And then we say that, we again stick to our statement saying that entropy total should be equal to entropy system plus entropy surrounding greater than 0. Then the process is spontaneous, or del S total has to be greater than 0, then it is spontaneous. Okay, now let's see what second law of thermodynamics reads. The second law of thermodynamics states that total entropy of a system and surrounding increases in spontaneous process. Alright, so we have got to now try and understand the final verdict about entropy. So final verdict says that change in entropy total, if it is greater than 0, then it is a spontaneous process. If it is less than 0, non-spontaneous process. Now mind you, we have brought in total, so even surrounding is involved there now. Alright, and total S and entropy total, if is equal to 0, then the process is in equilibrium. So we are going to carry this along with us in our next video, where we talk about Gibbs energy. Alright, so we will see how Gibbs energy says that we are more interested into the system rather than surrounding. So a new concept was introduced by Gibbs. Let's see and understand what it is. Alright.